Hi everyone. Here we are discussing about Laplacian operator, Laplace equation, application to electrostatic field and wave equations, vector integration, Stokes theorem and Gauss's divergence theorem. First of all, we are discussing about Laplacian operator. We already know about gradient, divergence and curl of a vector. Letting del operate on each of these quantities, we obtain the relations such as del dot del phi, del cross del phi, del dot del cross v, del cross v, etc. Among them, the expression del dot del phi is named as the Laplacian of phi. The expression del dot del phi, that is, the divergence of the gradient, is named as the Laplacian of phi. Del dot del phi is equal to dou by dou x into x cap plus dou by dou y into y cap plus dou by dou z into z cap into dou phi by dou x into x cap plus dou phi by dou y into y cap plus dou phi by dou z into z cap. That is equal to dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square. When phi is the electrostatic potential, we have del dot del phi equal to 0, which is Laplace equation of electrostatics. Next topic is the derivation of electromagnetic wave equation. We already familiar about the Maxwell's equations. So the following equations are Maxwell's equation in vacuum. We know that in case of vacuum or free space, current density J, rho and sigma will be 0. So the Maxwell's equations in that case will be del dot B equal to 0, del dot E equal to 0, del cross B equal to epsilon 0 mu 0 dou E by dou T, del cross E equal to minus dou B by dou T. Where E is the electric field, B is the magnetic induction, epsilon 0 is the electric permittivity and mu 0 will be the magnetic permeability. So, we are deriving the equation. So, taking the curl on equation 1D, we get del cross E equal to del cross minus dou B by dou T. It is numbered as 2. We have already know the relation del cross A equal to del of del dot A minus del dot del A, that is equal to del of del dot A minus del square A. Substituting this relation in equation 2, we get del of del dot E minus del square E equal to minus dou by dou T of del cross B. Then we know that del dot E equal to 0 from Maxwell's equation. So substituting this in equation 3, we get del square E equal to dou by dou T of del cross B. Then del cross B, we know that the value of del cross B from Maxwell's equation. So substituting the value of del cross B in equation 4, we get del square E equal to dou by dou T of epsilon 0 mu 0 dou E by dou T, that is equal to del square E equal to epsilon 0 mu 0 dou square E by dou T square, which is numbered as 5. This is the required electromagnetic vector equation. Next topic is vector integration. We have three types of vector integrations: line integral, surface integral and volume integral. First one is line integral. The integral of a point function along a curve is called a line integral. Let r equal to r of t be the equation of a curve. If phi and a are the scalar and vector fields respectively and dr is the vector increment of length, then we may encounter the integral along the curve C phi dr, integral along the curve C a dot dr and integral a cross dr, each of which being known as the line integral along the curve C that may be open or closed. The result of integration are respectively a vector and a scalar and a vector respectively. Then as phi is a scalar function and dx equal to dx into I cap plus dy into j cap plus dz into k cap, integral 1 immediately reduces into integral c phi dr equal to I into integral c phi of xyz into dx plus j of integral phi into xyz dy plus k cap into integral phi into xyz dz. It is numbered as 4. The three integrals on RHS of fourth equation are ordinary scalar integrals, and to avoid complications we shall assume that they are Riemann integrals. The integral with respect to x cannot be evaluated unless y and z are known in terms of x. Similarly, for the integrals with respect to y and z, this simply means that the path of integration c must be specified. Unless the integrand has special properties that let the integral to depend only on the value of n points, the value will depend on the particular choice of c. Then the line integral in 2 is most commonly used in vector analysis. It is called line integral of the tangential component of vector A along the curve C. An important example of line integral of vector function is the work done by a force, that is integral along the curve C f dot dr represent the work done by the force. If the integral C a dot dr is independent of path, then the vector field A of xyz is said to be conservative or non-curl vector field. Next one is the surface integral. Surface integral. If y a and a are scalar and vector fields respectively, the surface integral may be encountered as double integral phi ds, double integral a dot ds, double integral a cross ds. The result of this integration are respectively a vector, a scalar and a vector. The surface integral double integral s a dot ds is called the flow of flux of the vector function a through the given function s. For example, if a is equal to rho v, where rho is the density and v is the velocity of the fluid, then the surface integral s rho v dot ds denotes the amount of fluid flowing through the given surface in unit time. That is all about surface integral. And then volume integral. Let dy equal to dx into dy into dz denote the element of volume. As volume element dv is a scalar, there are only two possible volume integrals, that is double integral along v phi dv and double integral a dv. The result of integration are respectively a scalar and a vector. That's all about volume integral. Next topics are two important theorems, Gauss's divergence theorem and Stoke's theorem. It is often convenient to convert multiple integrals into others with fewer integral signs. This is done by two important theorems, Gauss's divergence theorem and Stoke's theorem. So first of all, Gauss's divergence theorem. It is a useful relation between surface integral of a vector and the volume integral of the divergence of that vector. It states that integral v dot d rho equal to integral del dot v d tau. In words, the surface integral of a vector over a closed surface equals the volume integral of the divergence of that vector integrated over the volume enclosed by the surface. Next is Stoke's theorem. Stoke's theorem enables us to transform the surface integral of the curl of the vector field A into the line integral of that vector field A over the boundary C of that surface and vice versa. Theorem states that the flux of the curl of a sector function A over a surface S of any shape is equal to the line integral of the vector field A over the boundary C of the surface. That is double integral curl A dot ds equal to integral A dot dr, where ds represent the infinitesimal element of surface area S and dr is an infinitesimal element of the boundary C of that surface. That's all about this video. Thank you.